Hi guys, today we're going to be looking at bivariate data and fitting models. So this sounds like kind of big and kind of scary, but this is actually really exciting. People always ask me, when am I going to use this in real life? And for me, I've always been in maths, I've always been in science, so it's kind of hard for me to justify sometimes when or why you'll use a particular branch of mathematics. This is so heavily used in science, I cannot even stress this enough. All you are doing when you're doing science is you're trying to find models, or you're trying to find, a method to the madness to fit your particular hypothesis. So this stuff is actually really exciting for me. So today what we're going to be doing is we're going to be using information technologies to investigate bivariate numerical data sets, and we're going to be graphing equations. All right, so I want you to go through and I want you to define those terms in your book. So we've got bivariate, as in bivariate data. I also want you to define what data is. I want you to define scatterplot, dependent variables, and independent variables. All right, so let's jump in. So bivariate data, bivariate, so two variables, x and y. So our independent variable x impacts on our dependent variable y. And we've already seen this. We know that the x goes across the horizontal axis and the y goes across the vertical axis. So we might say, for example, I know when we were in grade 7, we did stuff with toy cars. So like, for example, the number of winds on the toy car versus how far it goes. So if you wind the car 3 times, is it going to go further than if you only wound the car up once? So the distance the car travels depends on the number of winds. So the number of winds would go on our x-axis, and the distance that the car traveled would go on our y-axis. Okay, so we're assuming that there's some relationship between those two variables. So for example, this table shows the revenue from selling tickets for a number of different chamber music concerts. Represent this data on a scatter plot. So all you need to do, you're just going to plot it like an x and a y coordinate like you've done a bunch of times before. And eventually we start to see this sort of pattern. Okay. And we can kind of we can't exactly draw like a perfect line through this, but I'm going to kind of like make a little prediction here. Right. So I'm assuming that the more tickets that you sell, the more money that you are going to make. Right. That seems pretty common sense to me. Okay, but we can't say that. There's not necessarily the revenue that's causing, the ticket sold that's causing the revenue. It could also be something like the popcorn that's being sold at the thing, or it could be like drinks that are being sold, whatever. So it's not just the number of tickets sold that will indicate the total revenue, but it's a pretty good predictor of what the total revenue is going to be. So we can say that there's a strong positive correlation between the two variables. Now, correlation is not causation. Correlation is just a descriptive term, so it's not a mathematical term necessarily. It's not like a number value or anything, but we're basically just saying how strong or how weak the correlation is between the two variables. Okay, so the closer the points are to some sort of function, so in this case a linear function, the stronger that is. So we've got some examples of some slopes down here. So I've got a strong positive correlation, and I know that that's going to be a strong positive linear correlation because I could just about draw a straight line through all of those points there. Okay, so it's a very strong correlation. And it's a positive correlation because it's going up as we go across. Now, this is a weaker positive linear correlation, and you can kind of see that because you could draw a line through there, but it's not quite as close as what these points are here. So it's a weak correlation. When there's stuff all over the joint, we're just going to say that that's no correlation. That's fine, whatever. And then going back down the opposite way, now we can see that there's a weak, there is a weak negative correlation, okay? And we know that it's negative because it's going down. Right? And same thing with this one here. We know this is negative because it's going down. But again, we can see that this correlation is a lot stronger because these points are a lot closer to the line compared to these points over here. So I'll say it again. Correlation does not equal causation. I mean, sometimes it does, but you cannot ever make that assumption. That's the big thing with science, is that there's always these sort of underlying factors that we might not be aware of. That's why we have controlled variables in science, so that we can control those underlying issues that may be affecting our data. Say, for example, some people might really like chocolate Easter eggs. So the more chocolate Easter eggs, the fatter they get. Sure, But what you're also not seeing is that those people who are eating more Easter eggs are also eating more chips and pizza and chocolate. And so we have to control for the pizza and everything else so that we're not just assuming that the weight gain is from eating the Easter chocolates, because it's actually from eating the pizza and the chips and everything else. Okay. So really, really important. Correlation does not equal causation. I've also got some examples here of some correlated variables, okay? So just because variables are correlated does not mean that they are actually related in real life or that one causes the other. Perfect example, the number of people who drown by falling into a pool and the number of films that Nicolas Cage has appeared in. And you can see they are very well correlated. They fit the pattern very, very well. But it doesn't really make sense to say that people drowning affects the number of films that Nick Cage has been in. Also doesn't make sense for us to say that Nick Cage appearing in films causes people to drown into pools. That's not how it works. They are very well correlated, but that does not mean that one causes the other one. There's also a positive correlation between things like sour cream sales and motorbike accidents. So we can see that as the number of sales of sour cream go up, the motorbike accidents seem to go up as well. And when the number of sour cream sales go down, the number of motorbike accidents go down as well. So maybe, who knows, maybe people buy more sour cream and they're throwing it on the road and that's what's causing people to slip up. But it doesn't usually make sense to say that, you know, the number of sales of sour cream causes motorbike accidents. And similarly, the motorbike accidents are not causing sour cream sales, unless people are eating because they're sad from all their friends and family dying in a motorbike accident. Anyway, so there's a whole bunch of these online. If you go up and look on correlation versus causation, there's a whole bunch of funny memes. Go check them out. Okay, so we need to be very careful with the language that we are using to describe the relationship between variables. Okay, so we can't say, for example, that Nick Cage causes people to drown. What we're going to use instead is we're going to use the language. So there is a strong positive correlation. So see how I've used that word strong? Okay, because that tells me how close it is to fitting that pattern. It's positive because it was going up as we went across, and it's a correlation because we don't know what's causing what or the other thing. And the thing is too, like with correlation, there could be something else that's sort of impacting both of those things. So for example, if we were looking at the prices of apples and the prices of bananas, and we say, oh, wow, the prices of apples are going up and the prices of bananas are going up. Well, the apples going up must have caused the bananas going up. Well, that's not true at all. What's actually causing it is there's been some sort of stock market crash behind the scenes, right? And so everything is becoming more expensive. It's not the apples or the bananas that have anything to do with it, okay? So we have to be very careful with that language that we are using. Same thing with motorbike accidents, right? Causing sour cream sales. We can't say that it's caused by. We have to use that word correlation. So again, there is a strong positive correlation because the points are very closely aligned. That's why it's a strong correlation. It's a positive correlation because as one goes up, the other goes up as well. And it's a correlation, not a causation. All right, so now we're going to jump in and we're going to have a go at some questions. And these are actually really simple to do. So I'm going to, first of all, we're going to find the difference between the independent and the dependent variables. So I'll get you to pause the video and I'll go through the answers. Okay, so let's jump in. So for each of the following pairs, decide which is independent and which is dependent. So really, let's just use the language something depends on something, and then we'll be able to figure out pretty easily which one is the dependent and which one's the independent variable. So the number of hours spent studying for a maths test and the score on that test. So do you think the score depends on the number of study hours, or do you think the number of study hours depends on the score? Well, I think that the independent variable is going to be the number of hours spent studying, and then I think that the dependent variable is going to be your test score, okay? All right, the next one, daily amount of rainfall and daily attendance. So does the daily amount of rainfall depend on how many people have attended the botanical gardens? No. The number of people in daily attendance depends on the amount of rainfall. So the amount of rainfall is the independent variable, and the dependent variable is daily attendance. For 1C, the number of hours spent per week in a gym and the annual number of visits to the doctor. Now, I'm assuming that these people are not getting injured because Lord knows I have been injured so many times at the gym. So Well, I'm going to assume that the number of hours spent per week in the gym is going to be the independent variable, and the number of doctor's visits is going to be the dependent variable. And lastly, the amount of computer memory taken by an essay and the length of the essay in words. The length of the essay in words is going to be the independent variable, and the amount of computer memory taken up by that file is going to be dependent. Okay, we've got another couple of really easy questions here. So state the type of relationship. So we're going to be using that language strong, weak, correlation to describe these relationships. So again, I'll get you to pause the video and then I'll go through the answers. Okay, so this first one, we can see very strong linear correlation because that's basically a straight line going through there, if I can draw that. For this one here, there's no real correlation at all between the two variables. And then this one, we can see that this one is sort of going like kind of down. Why can't I draw? I'm going to get the arrow. That'll be a bit easier. There we go. And I'm actually going to say that this is still a fairly strong correlation. It's not a perfect correlation like this one seems to be, but all the points are still pretty close to that line. All right, the last one, Eugene is selling leather bags at the local market. During the day, he keeps records of his sales. The table below shows the number of bags sold over one weekend and their corresponding prices to the nearest dollar. So construct a scatter plot of the data. So again, let's just think about this. So does the price of a bag depend on the number of bags sold, or does the number of bags sold depend on the price? I think the number of bags that have been sold is going to be the dependent variable, and the price of the bag is going to be the independent variable. So all we're going to do is we're going to plot this, and then we're going to state the type of correlation between the two. So I'm going to do that off screen. Okay, so I've done my very rough drawing over here. It's going to be a little bit easier for you guys because you're going to draw it in your grid books and you're going to use a ruler and everything like that. But I've made sure that I've included all the key elements of this graph. So I've got my sketch, I've got my axes, I've got my labels, and I've got my title on there. So I've constructed my scatter plot and I've put in all my data. Now I need to state the type of correlation between the two variables. So you can see that this is going down, right? So this is going to be a negative correlation. This is a negative correlation because as the price goes up, the number of bags sold goes down, okay? So the conclusion is the more expensive the bag, the less of them that are going to be sold, or the cheaper the bag, the more that will be sold. So if you wanted to make a profit, you can sell the bags for a cheaper price. So that might be my conclusion from this. So I want you to go through that chapter, so chapter 13.2, and just pick 3 or 4 of those sort of trickier questions. So from question 4 onwards, it's not a really super difficult chapter, but we're going to use this information now for to find the lines of best fit, and this is where it starts to get a little bit trickier. All right, I'll see you in the next video. Bye, guys.